In this setup, we will explore the behavior of three masses undergoing collisions. Initially, mass A moves to the right with a velocity VA, while mass B moves to the left with a velocity VB. Mass C is stationary at first. Mass A then collides with mass B in a perfectly elastic collision. After the collision, mass A rebounds to the left with a new velocity VA prime, while mass B continues moving to the right with a new velocity VB prime. Eventually, B collides with C, and after the collision, both masses B and C stick together, and they move with a new velocity denoted by VBC prime. We need to determine the final velocity VBC prime after the second collision. The known quantities are the initial velocities VA, VB, and the velocity of A after the first collision VA prime. Now let's break down the mechanics behind these collisions. Since the collisions are perfectly elastic, we use the principle of momentum conservation, which states that the total initial momentum equals the total final momentum. We apply the momentum equation in the indicated direction. Initially, before the collision, the total momentum is MAVA minus MBVB. And after the collision takes place, the total momentum becomes minus MAVA prime plus MBVB prime. Then we just solve this equation to determine the velocity of mass B after the collision. We now apply the momentum conservation equation to the second collision. Mass B is currently moving to the right with a velocity of Vb prime and mass C is stationary, which means a velocity of 0. After the collision, they stick together, therefore its momentum is a sum of its masses Ma plus Mb multiplied by the unknown velocity which is denoted by Vbc prime. After simplifying this equation, we can substitute the value of Vb prime, which we found earlier, in order to determine the new velocity of the combined masses. This example highlights the fundamental principle of momentum conservation and how it can be directly applied to solve collision problems.